Hi class. So now let's talk about the concept of stability. So this is section 7 in chapter 6. And we're going to use slide number 30 as an example. And this is also an example of problem number 8 on the homework. Okay, and so what we've got is I've given you an atmospheric layer. So these are different layers within the atmosphere, and we're going to determine whether the air is stable or unstable at these specific layers of the atmosphere. Okay. Now we've got what's called an environmental temperature. That's the actual atmospheric temperature. So if we sent up a weather balloon with an instrument package attached to it, these would be the temperatures that it would have measured at the specific layers of the atmosphere. And so we want to determine then, is the atmosphere stable or unstable at these specific layers given these temperatures that we measured? Okay, and so what we're going to have to do is calculate an adiabatic temperature at each of these layers. So as I mentioned in the notes, the adiabatic temperature here is sort of like the temperature inside a hot air balloon, whereas the environmental or atmospheric temperature is the temperature of the air outside the hot air balloon. Okay, so if the temperature inside the hot air balloon is warmer than the temperature outside the hot air balloon would rise, and we'd consider that an unstable atmosphere. Okay, and so the temperature inside the hot air balloon is the adiabatic temperature that we're going to calculate. It's the temperature of a parcel of air, and that parcel of air is analogous to a hot air balloon. All right, so let's start off at the bottom where we measured a temperature of 29 degrees Celsius, and we want to calculate what the temperature at the 800 meter level is going to be. Okay, and so the first thing we got to do is we got to determine whether that air, when it rises, the pressure decreases, the air expands, the density decreases, the temperature decreases. Is that temperature going to decrease at the dry adiabatic lapse rate or the moist adiabatic lapse rate? Okay, well, notice that I gave you in this problem that the lifting condensation level, the level to which we have to lift the air for condensation to occur, takes place at 1500 meters. So if that's the LCL, that's where relative humidity reaches 100%. So at the surface then, that implies that the air is unsaturated, so we're going to use the dry adiabatic lapse rate. So the temperature at 800 meters will be the temperature at the surface, 29 degrees Celsius, minus, because the air is rising and cooling, the dry adiabatic lapse rate, 10 degrees C per 1,000 meters. And we're going from the surface up to 800 meters. So 800 meters minus 0 meters. Okay, so that will give us 29 degrees C minus 10 degrees C per 1,000 meters, but we're only going up 800 meters in this step. So we're going to subtract 8 degrees C, and so our temperature at 800 meters will be 21 degrees Celsius. So adiabatic temperature will be 21 degrees. Okay, now let's take a look at, is that air at 800 meters, is that stable or unstable? So in this particular case, the temperature of the atmosphere is 19 degrees C. In other words, the air outside the hot air balloon is cooler than the air inside the hot air balloon, or vice, if you want to look at it the other way. The air inside the hot air balloon is greater in temperature than the air outside the hot air balloon, and therefore that is going to give us an unstable atmosphere. So here at 800 meters, the air is unstable. Okay, now that's just at this layer. Let's take a look now at 1500 meters. And so we'll go back here. And now we got to calculate the temperature at 1500 meters and see if that layer of the atmosphere is stable or unstable. And to do that, again, the first thing we got to do is to determine whether that air is going to rise and cool at the dry adiabatic lapse rate or the moist adiabatic lapse rate. Well, we haven't reached the lifting condensation level yet. We're going from 800 meters to 1500 meters. So the air is still unsaturated. Okay, it hasn't reached saturation yet. It hasn't begun to condense out its water vapor. And so here we would once again use the dry adiabatic lapse rate. And so our temperature at 1500 meters will be the temperature at 800 meters, 21 degrees Celsius, minus, because the air is rising and cooling, it is rising and cooling at the dry adiabatic lapse rate, 10 degrees C per 1,000 meters. And we are going from 800 meters to 1,500 meters. So 1,500 meters minus 800 meters. Okay, and so now our temperature will be 21 degrees C minus 10 degrees C per 1,000 meters. We're going up 700 meters, so that means our air is going to cool by another 7 degrees C. And so at 1,500 meters, our air temperature will be 14 degrees C. Okay, and so here we see that the air inside the hot air balloon is still greater than the temperature outside the hot air balloon. And so as a result, if the air inside the hot air balloon is warmer than the air outside the hot air balloon, that would make for an unstable atmosphere and the air would want to continue to rise. Okay. All right, so that takes us to 1,500 meters. Okay, now we've reached the LCL. We can draw a little cloud here if you want to as a reminder that we've hit the LCL. So cloud's forming here. And now let's take a look at what the temperature of the air is going to be at 2,000 meters. Okay, and so we have reached the LCL. Relative humidity is 100%. We've got condensation taking place. And so as a result, when this air rises, it's going to rise and cool at the moist adiabatic lapse rate. Okay, so let's see what the temperature of the air will be at 2,000 meters. Okay, at 2,000 meters, we start off with the temperature of the air at 1,500 meters. It was 14 degrees C. It's still rising and cooling, but now it's going to cool at a slower rate. We're going to switch to the moist adiabatic lapse rate, 6 degrees C per 1,000 meters. And we are going from 1,500 meters to 2,000 meters. Okay, and so that will give us 14 degrees C minus 6 degrees C per 1,000 meters. We're going up 500 meters, so that means the air would cool another 3 degrees Celsius, and that would give us an adiabatic temperature, or the temperature inside the hot air balloon, of 11 degrees C. So I'll put 11 degrees C up here. All right, so our temperature of the atmosphere at 2,000 meters was 12 degrees C, and that is greater than the temperature inside the hot air balloon, or flip it around. The temperature inside the hot air balloon is cooler than the air outside. If it's cooler, then it's going to be less dense, and that means that the air at the 2,000 meter level is going to be stable. All right. Okay, one more level to take a look at. We're going to go up to 3,000 meters, and we're going to assume that the air is remaining saturated. Okay, so clouds would be at all of these levels here. up to our 3,000 meter level at least. If that's the case, the air is saturated, so the air would cool at the moist adiabatic lapse rate. The temperature of the air at 3,000 meters, okay, would be equal to the temperature, the adiabatic temperature at 2,000 meters, 11 degrees C, minus, okay, the air is still cooling as it rises. It's cooling at a slower rate, the moist adiabatic lapse rate, because the air is saturated, 6 degrees C per 1,000 meters. Okay? And we're going from 2,000 meters to 3,000 meters. So 3,000 meters minus 2,000 meters. Okay? And so that will give us an adiabatic temperature of 11 degrees C minus 6 degrees C per 1,000 meters, and we're going up 1,000 meters, so that would be minus 6 degrees C. So that would give us a temperature, an adiabatic temperature of 5 degrees C. Once again, now the temperature inside the hot air balloon is greater than the temperature outside the hot air balloon. So 4 degrees C is less than 5 degrees C. Okay. In other words, the temperature inside the hot air balloon is warmer than the temperature outside the hot air balloon, if you want to look at it that way. And so as a result, this air, once again, is going to be unstable at this layer. And it's not uncommon throughout the atmosphere to have stable layers and unstable layers. And so this example, there's nothing wrong with it. And so even though you might have a stable layer at 2,000 meters, it could be unstable above and below that layer. Okay? So there's an example of number 8 in the homework, and hopefully it gives you an idea of the concept of stability. If the air is unstable, it's going to want to rise. If it's stable, it's not going to want to rise. Okay? All right. So we'll finish off the rest of this chapter yet this afternoon, and I'll email you in just a little bit. Take care. Bye-bye.